All right, let's start this new unit on inference, where we want to take one sample and then see what kinds of things we can infer about the whole population. We've already kind of been talking about that as we've done sampling distributions, but we're going to go a little bit more in depth, quite a bit more in depth, and this is the crux of all of statistics. So here we go. So let's talk about this. What is a confidence interval? That's where we're going to start. And what's its purpose? What does it do for us? So here is a picture of the train in downtown metropolis of Aledo. Okay, there's the silos there behind it. Here's the train. So do you know the true proportion of times that Aledo High School students who live on the south side of the Aledo railroad tracks get stopped on the way to school? I have no idea. How could we possibly really know what that is for the whole? I mean, like the true overall whole population amount. Okay, that's where we're headed with this. Do you think that, what do you think that true proportion of high school students who, I don't know, whatever, what do you want to know? The proportion of high school students who have a birthday in September. I mean, we could probably comb through the data to do that, but the proportion of high school students who prefer Pepsi to Coke, I don't know. Whatever it is that you are interested in knowing, how could we do that? Um, what do you want to estimate about a population that is not known? Well, how do you think we might can do this? Well, hopefully you imagine we can take a sample. So we're going to talk about that. Now, in one sample estimate, which is called your statistic, okay, is your statistic enough information to say, bam, here's what I know that the population is, the value of the population for that is? And we've talked about that. No, you cannot do that because one sample may or may not be the population amount. Because of sampling variability, you're going to get some data a little higher or lower or whatever. Now, are there any special qualities, traits, or characteristics that we might need to consider when attempting to make an estimate for that whole population? And so this was just a question for you to ponder and to think about. I mean, I personally want to know, um, how can I tell how far away my estimate is from the true population amount? How much is that? Is it within sampling variability? How do I know? Um, so let's see where we go from here. All right, a confidence interval in statistics is a type of estimate that we are going to learn how to compute from a statistic, our little p hat that we get from observed data we collect. So this proposes a range of plausible numbers. So we're going to get this range, a lower bound and an upper bound from that one sample value that we think might include the population value. So we get this interval from here to here that we think will contain the population parameter. Population parameter range from our population parameter from the range we got from our statistic. All right. The interval has an associated confidence level. So we're going to learn what this confidence level is. I'm 95% confident that the true proportion is within this, or I'm 90% confident. Anyway, so here was something interesting I thought was funny. Taking a look at tomorrow's weather, the high temperature will be between 40 below zero and 200 above zero. And then Garfield says, whoa, this guy's never wrong. Okay. Well, I think I could be probably 100% accurate if I had that gargantuan of a range of plausible values. But is this very informative to talk about a temperature between 40 below and 200 above. Okay, no. So let's see how we can narrow that interval down um, to, to a more reasonable estimate. Okay, so we're going to do an activity. So I hope that you have this. Maybe you have some Hershey's Kisses, or you can go and get some. In this activity, we're going to create a confidence interval to estimate the true proportion of times that Hershey's Kisses land on their base as opposed to their side. So to do this, we're going to take Hershey's Kisses and we're going to shake them up to randomize, and we're going to drop them. And we're going to count how many times the kisses land on their base. And then from that, create this range of plausible values, a confidence interval. So to take your sample, gather 5 Hershey's Kisses in your hand, shake them up and drop them from about 6 inches above your desk. Count the number that land on their base and repeat this 20 times to get a sample size of 100, recording your results below. Okay, so I did this. Here are results I got. I want to go and I think I have some of these. I'm going to get these Hershey's Kisses. We're going to actually do this lab. In fact, I'm going to be going to Walmart later, and these were other ones I had happened to have. Okay, so these were hugs. Okay, so here are the hugs. You can see, and I'm going to shake them up and then drop them. And let's see, 2 of them, 2 out of 5 landed on their base. So then I would record that amount, and I'm going to toss these 5 20 times. So when I do 20 times of this 5, that makes a sample size of 100. So I'm going to do this 20 times and see. And so I did it, and I had 32 times out of my 100 drops that it landed on its base. 32. Okay, so what is this population that we're going to of interest? So our population is all Hershey's Kisses. And we're wanting to know the proportion of the time that all these Hershey's Kisses, I might eat one now, will land on their base. All right. What is your sample? Well, it's my 100 tosses of my Hershey's Kisses, or hugs. It was a hug. All right. So the p hat that I got, my p hat was 32 over 100. That's 0.32. Now, I had some other friends who had done this last year, and they had gotten these numbers. So compare your p hat with others in your group. Do you all get the same answer? No, because of sampling variability. Of course, we know that with sample to sample, you get different data than me because of sampling variability. So now, let's take a look at what we have going on here. A confidence interval takes your estimate, your p hat, and your estimate of the true proportion of Hershey's Kisses that land on their base, your p hat, along with this margin of error. Okay, you might have heard of that in polling, in political polls. And so then this is going to make this range of plausible values that you feel fairly certain will contain that true proportion, that population amount. You don't know exactly what it is, but you're going to estimate it. So here's kind of an example. Here's what a confidence interval looks like. So see, here we have this. Here's a graphical representation of it. So we would draw a dot on a number line of where our point estimate is, our p hat. Okay, and then we would have the lower bound, which will be we'll compute that. We go to take this margin of error, we'll compute that as well, and it'll then take us down, we'll subtract it to get to the lower bound, and then from our point estimate, our p hat, we'll add that margin of error to get to the upper bound. Okay, now look at what this might look like. If the population p, which this is just an abstract imaginary line. We do not know what this line is, okay? And so bunches of people get different intervals because, see, they get these little black dots. Those are other people's p hats, and then they make their interval. So you get these ones. Now look at what has happened. All of these people's samples, these top ones, the dot is the p hat, and then that margin of error takes you to the lower bound and the upper bound. All of these ones actually captured or contained that true population answer. But there were, and there will always be, a few. So these ones down here, here's what it would look like if you got a p hat, that when you made your interval, it didn't actually capture or contain that population amount. Now, that doesn't happen very often. It's showing here like 4 out of the 10. Well, no, that does not happen 40% of the time. And we'll talk about how frequently that happens as we go through this unit. Okay, so let's talk about what makes this margin of error. What is making this range of plausible values? So there are a couple of things that will contribute to the size of that margin of error. Sample size is one of them. And then this other thing called the confidence level, you can see down there at the bottom, confidence level. So those are two things that will make up that little whisker, that margin of error that goes on either side of your p hat. Okay? All right, so let's talk about it. So, why do you think that sample size might affect the size? Well, it has to do, again, with standard deviation. Our standard deviation, of course, your p times your 1 minus p over n, and then you square root it, okay? So that's going to give us, that means that as your sample size gets larger, then your standard deviation will get smaller. And then you know what's going to happen? That whisker is going to get smaller. So then we're not estimating from negative infinity to positive infinity. We're being able to estimate and have a smaller range of plausible values. So sample size going up is a good thing. So let's do that. Let's take my number, my p hat of 0.32, and go estimate that. Now, calculate your standard deviation. Let's look at this formula. Do you remember this formula has p times 1 minus p over n, and then you square root it. But what is that p? Do we have true p to be able to put into this formula? No, we do not have true p, because we were supposed to be, that was the whole purpose of this activity, is to estimate and potentially, estimate and find a potential location of this true p. So we don't have true p. So if you do not have true p, the best it can be is if you have true p, but if you do not have that, then you can estimate with your p hat. Now, when you use your sample p hat instead of the population p, then which makes the standard deviation, this is now called this thing, it's just a little different wording, and we just want to be kind of aware of it. It's not a major deal, but be aware that I'm using a sample to make this, and so it's a little off, okay? So it's the standard error of a statistic. Instead of that standard deviation, sometimes it'll be referred to as this standard error of the statistic, because I used my p hat, because I don't know what p is, so I did the best I could. All right, so here is my standard deviation, or my standard error. My 0.32 times the 0.68 over 100 square rooted is 0.047. Okay? So right at about a half. All right. Either way. So now, okay, so now we're going to then talk about this thing called a confidence level. Because we're going to end up going, in the long run, we're going to end up going, hey, let's make a 95% confidence interval, or let's make a 90% confidence interval. And I want to be 90% confident that that the true proportion is contained within my interval. Or I said that wrong, that my interval has captured that true proportion. Okay, So let's take a look over here at what some of these intervals look like based on a confidence level. So if we take a look at this, you can see this white section here in the middle is what a 90% confidence level or interval would look like. Then let's see. Look what happens. If I go wider, that's from here, this little light gray area from here to here. That's making the 95% confidence interval. Okay. From here to here. I need to draw that from here to here. Okay. Now, what about a 99% confidence interval? That's going from here all the way down to here. So I think you can see that if you are more confident that you captured the true proportion, then it's a bigger interval. Okay, you are more confident. In fact, you can't really, if you, in order, only way to be 100% confident is you're going from negative infinity to positive infinity. You have to be 100% confident, and that doesn't tell us much. So we can see that as the middle area gets wider, that we have that higher confidence. And really, what happens is that higher confidence is what's driving that going wider because we are more confident that our interval captured or contained that true proportion. Okay, what do you notice about the numbers at the bottom? What do these things look like? Okay, well, I hope that you can tell that these are z-scores. These are based on how many standard deviations away those intervals are from the mean. Okay, so let's now put all of this into works to do some computing. Okay, so let's actually look at how to compute that. So let's consider what we're going to do with ours is make 95% confidence intervals. Okay, so think about that means 95% is what's in the middle. So if 95% is what is in the middle, then what remains on the outside edges? So what remains on the outside edges is 5%. We'll split it though between the two tails. So that makes 2.5% on each one of those outside edges. So 95% in the middle makes 2.5 on the outside edges. So that's how now I can compute this critical value right here. I can say, what is this z-score with 2.5% below it? And so that is done with inverse norm of one tail. So to get our critical value, we're going to be told the percent of confidence, and that confidence level is what's in the middle. And then we're going to inverse norm of one tail to get that critical value. So I had this song, and I haven't made a video of it yet. I need to, but I just haven't had time. And this year I certainly don't have time. Here it is, 9:30. I'm up here making my video because I just got your packets copied. But so look here. Here's kind of like the big deal because I was having students think the critical value for 95% was 0.95. Wrong, wrong. The critical value is not 0.95 for 95% confidence. You need to find the critical value while you may use the confidence level. This confidence level is not your critical value, your Z star, this critical value. The confidence level is what's in the middle. You need to inverse norm one tail. Inverse norm of one tail, inverse norm of one tail. Okay, now, so you could pause and then come on down here and try this yourself. Draw what it would look like for your middle. In fact, I'll put this up here so I'm not showing everything. So draw the middle percent. So if you want to be 90% confident, draw a picture, put 90% in the middle. Think of then what's on each of those tails, and then compute inverse norm of one tail. Now, when you do that, what do you notice? Once you do that inverse norm of that one tail, it will always give you that lower critical value. But we know that the margin of error has two sides. Okay, it has the negative and the positive. So we have those critical values, and that's how we have the positives and the negatives. All right. So you can compute those, and then we can talk. What do you notice about those critical values as the confidence level is increasing? Again, those critical values are getting bigger because the interval is getting bigger. So that's what I had. As the confidence level gets bigger, the interval gets wider, which means that critical value is getting bigger because it's getting farther away from the mean. Okay. Now, that margin of error determines how wide or narrow your confidence interval is. It's found by multiplying the critical value by that standard error, that standard deviation from your p-hat. So let's make 95% confidence intervals with our number, our hugs, okay, that fell on their base, 0.32. Here we go. What is our critical value? For our critical value was inverse norm of one tail. That was 95% in the middle, inverse norm one tail, positive and negative 1.96. So then we had that standard deviation of the p-hats, the standard error from before. So the margin of error is those two things multiplied together. And that is what makes the whisker. So that margin of error is that 1.96 times the standard deviation of the p-hats, 0.092. So let's finish this out. Your confidence, because see, we had the positive and the negative. We had that you got your p-hat in the middle, and the interval gets made from adding up the margin of error. Here is the margin of error. So you take your statistic, your p-hat, you add up this margin of error to get the upper bound, and you subtract this margin of error to get the lower bound. So look at what this looks like. Here it is. My p-hat was 0.32, and then I'm going to add my margin of error to get the upper bound, and then my p-hat was 0.32, and I'm going to subtract that margin of error to get the lower bound. That is my interval from 0.228 to 0.412. So this is saying that I am 95% confident. I'm 95% confident, and we'll talk about what that confidence level means in another lesson later. We'll get more into it. But I'm 95% confident that the true proportion, of kisses that will land on their base is between, like for the whole population, is between 22.8% and 41.2%. And I think we're going to stop right there because your assignment that you're going to do is going to have you then just practice. We'll get into some other questions later, but your assignment that you're going to do is going to have you just practice that. So if you scoot on over to whatever page that is for your lesson, I can't tell, page 9. Okay, so here you go. This is some context here. We have 100 coins, and the probability of landing on heads is 0.73. So that's my p-hat. Okay, construct a 90% confidence interval for that true proportion. So we did a sample, and we got 0.73 and as our sample results. And so now then you're going to figure out. So here's we want 90% confidence. Draw your picture and put your 90% in the middle. Okay, which after you put 90% in the middle, then that puts, what is that, 5% on the outside edges. So you're going to inverse norm 0.05, inverse norm of one tail. So our critical values are going to be the positive and negative 1.64. Okay. Now, then, here it works you through here. Compute your standard error. So you're going to do the square root of that 0.73 times the 0.27 over our sample size, which in this problem was 100. Once you find that, then you're going to do the rest of your math. Your statistic, that's your p hat. So that's your 0.73. And then you're going to add up this margin of error. Well, this margin of error is the critical value times whatever you get from that. Okay? And that will give you the upper bound. And then you will get the lower bound by doing your statistic minus that margin of error. Okay? Same thing. So be adding it up, subtracting it down. And then you put your answer like an ordered pair. Okay? Where your p hat's right in the middle, but you have your lower bound and then your upper bound. So then in context, how you would write your answer is you're going to say, I am, in this case, it was 90% confident that the true proportion of whatever this is. What's the context of this problem? The true proportion of times this European coin lands on heads. True proportion of times, the proportion of times this European coin lands on heads is between, and then you have your this percent and this percent, okay, whatever that is. All right. And so then now you're going to create a few more of those and go through the motions of creating those. I think there's two pages. All right. So, in summary, that was a big lesson. That is your confidence interval, what it is, what it does for you, things that are involved, computation, and this is just the start of getting the ball rolling on inferences in statistics. All right. I will meet you back here tomorrow and we'll finish the lab and talk about some more components to it.